I'll present things that are published, some that are in the process of being published. The website is not very good, but at least its merit is to have all the papers. So if you go to www.nanophotonics.ch, you'll find all the publications, and of course, drop me a note or let's chat, ask questions. I will check actually if you remember what I've been talking about from time to time, and I'll be also looking forward to taking part in the poster session later on. So that's the menu. If it works, does it work? Yes, it's a bit of a long menu, so let me just start by talking about plasmonics. And I think the simplest way to try to understand what plasmonics is to look at the light scattered by a small particle. We have a small particle here. It's described by its refractive index. If we do electromagnetics, we're going to say actually it's described by its permittivity, epsilon. And what's very important is that the permittivity depends on the wavelengths. Every material is dispersive. You've also seen that in some of the presentation this morning where the color would change depending on the wavelengths. And so the permittivity changes with the wavelengths. And if you illuminate a small particle, let's say small metallic particle, for example, like silver, and you compute the amount of scattered light, then this comes out of this formula, and I think this is the only formula in the talk, so bear with me for that. In that formula, you have two terms. The first term depends on the radius of the particle, and it's quite obvious a large particle is going to scatter more light than a small one. But what's interesting in that first part is that you also have the wavelengths here. And you see that we divide by the wavelengths. This means that if the wavelength is small, you're going to have a lot of scattered light. And this is the reason why the sky is blue. The sky is blue because when you look up in the sky, you look at the scattered light. And among the wavelengths that our eye can perceive, the blue is basically the shortest wavelengths. I can see a few of you being puzzled and saying, but it's not true, or I can see violet. So why isn't the sky violet? And I leave you to ask this question tomorrow to Professor Rizzi, because he's going to be talking about the physiology of the eye. So the sky is blue because we have strong scattering at short wavelengths here. When we do plasmonics, we actually deal with this part of the formula. And in the formula, we have only the permittivity. And you see you have epsilon, the permittivity, +2. So the next ingredient I need to take into the game is the permittivity of metals. Metals, and these are experimental data from Johnson and Christie in silver, metals have a permittivity which real part, so that's the red line here, is negative. So there will be a specific wavelengths where the permittivity here is going to be -2. And if I have -2, that's going to be -2 + 2, so it's going to be 0. And you certainly know that dividing by 0 makes things very, very large. And indeed, at this wavelengths, around 350 nanometer, there is a huge peak in the scattered light. So a lot of light is scattered at this wavelengths, and this is what we call the plasmon resonance. I'll come back to the name in a minute. Now, this, when we look at the formula, we should think, well, this should be extremely thin and narrow. It should be like a singularity. But we see it's not a singularity. It has a certain width. And the reason for that is that actually the permittivity has also an imaginary part. This imaginary part accounts for the losses in the metal. It's the blue line here. It's small, but it's still significant. And that's the reason why here we have some width in that resonance. So we have a nice little theory, which is that a small silver particle is going to be blue because it's going to scatter the light, especially in the blue part of the spectrum. And when you have such a nice, simple theory, of course, you should try to confront it to the experiment. And that's something we did a long time ago when I was at UCSD, where we looked at colloidal silver. So these are silver nanoparticles. They all have the same size, 50 nanometer. And if you look at them under dark field microscope, you see that indeed they are blue, but you also see that some have very different colors. Some appear green, some appear yellow, some appear red. And actually, about 10 years ago, it was really not understood why this was the reason. Well, it's probably more like 20 years now. There was a very good technician in San Diego, and he managed to take exactly the same sample and look at it in electron microscope, and then resort to the large magnification you have from electron microscope. And there you see the blue one, indeed, is like a nice little sphere. But this one, which is green here, turns out to be polygonal. And this one, which is red, actually here, is a triangle. So basically, the shape of the particle is going to play a very, very important role. So, of course, I can hear maybe some of you are doing optics. They're going to say, well, it's very simple. This is just a resonance effect. We know that if we have a resonator, the shape of the resonator, like a Fabry-Perot, since we are in France, would have different resonant wavelengths depending on the thickness of the Fabry-Perot. But what's very puzzling is that this is actually for particles which are much, much smaller than the wavelengths. They are about, the wavelengths here is going to be 600 nanometer, the particles are 50 nanometer. And normally when you have a resonance, you need to have a similar wavelength as the size of the object. If you are in your bath and you want to make a tsunami, you're not just going to wave your arms around and make little wavelets. You're going to move forward and backward in your bath until you create a wave which has the same wavelengths as the bathtub. But here it's not the case. It's something very different that happens. We tried actually then to understand, and yes, indeed, it was more like 20 years ago, to understand what was going on, looking at particles from the highest symmetry, decreasing the symmetry, and even decreasing further the symmetry, triangle particles which are quite regular and then have a very high perpendicular to base ratio. And we observe that actually when you decrease the symmetry, you have a lot of additional modes that appear, which explains that when you're going to scatter light on this particle, although you would think it should be blue, it's going to appear red, for example, for this triangular particle. So it's the shape of the particle, and the shape of the particle is going to control the way the electrons move inside the metal. So what is resonating in this system is not so much the light, which has a very long wavelength, but it's the electrons. And as we will see, to have a good plasmonic material, you need to have a lot of free electrons. And if you excite these resonances, so for example, here for this triangular particle, very tiny, the base is 10 nanometer, the perpendicular 20 nanometer, we see different modes. This is a log scale to see the different resonances. And we see that also the field distribution around the particle is very, very different depending on the wavelengths. So this fundamental mode, so the mode at the longest wavelengths, it produces a very strong, I can say, a confinement of the light close to the corner of the particle. So this is the amplitude of the light. The incident light has an amplitude of 1. And we see that here, close to that corner, it reaches about 400. So it's a huge amplification. And if you change the wavelengths and excite another of this plasmonic mode, you have something quite different, whereby we have here a very strong field, but next to it is much weaker field and also a more complicated pattern. But this field magnification, field enhancement is really very, very strong. And there is a full field of plasmonics that deals with utilizing this very strong field enhancement and putting molecule on these nanostructures and looking, for example, at Raman spectroscopy or fluorescence enhancement caused by this very strong near-field enhancement. So the near-field enhancement is called by the fact that in the metal we have free electrons, and these free electrons, they get confined in specific position within the structure and produces very strong field enhancement. So unfortunately, we don't have many materials that will work for that. There are only a handful, a very short handful of metals that are plasmonic metals. Actually, these metals, they have a pretty name. They're called coinage metals. Coinage, it comes from coin. So these are the precious metals that we use for making coins, like gold, silver, but also aluminum, copper. And the characteristics of these metals is that they have a lot of free electron, at least 10 to the 22 free electron per cubic centimeter. And as a consequence, when light comes onto the metal, the free electron starts to be shaken around. And depending on the geometry of the particle, then the electrons are confined in specific location of the structure, producing this very strong field enhancement. So each of these metals, of course, will have a different permittivity, like we've seen the permittivity for silver, which produces a resonance in the blue here. Gold, which is the metal of choice, it will have a resonance in the red or even in the infrared. And then copper is not much used, but we'll come back to copper later in the presentation. It's in the orange. And aluminum is more in the blue, in the violet, or even in the ultraviolet. It's been considered also for plasmonics in the ultraviolet part of the spectrum. So that's this very brief introduction to plasmonics. I think the key thing to remember is that if you look at these plasmonic metals, if you take bulk, if you take a very large bar, like a silver bar like this one, it will have a given appearance. It will be grayish if it's silver, it will be yellow if it's gold. But if you make nanostructures out of this material, then you have a huge diversity of effects that you can observe, and these effects are going to depend on the geometry of the structures. So at this stage, it's also customable to say that, by the way, our ancestors, when they were building cathedrals, they used to put some little nanoparticle of gold in the glass paste. And these nanoparticle of gold, they will make beautiful plasmonic resonance, and they would make this very strong color that we can still enjoy today. And that seems actually quite reasonable if you think about it, because we know that chemical colors are not very stable. They faint very rapidly if we expose your, say, an old manuscript to light. But these stained glass windows, obviously, they've been around and they've been exposed to light for centuries, and still they have very nice, strong colors. So maybe they are made out of plasmonic nanostructures. I'll come back to that at the very end of the talk. So let me recap. So what have we learned so far? It's for you to tell me. I know it's very nasty after digesting a nice lunch. So we've looked at plasmon resonance. They will depend on the shape of the nanostructure, and they will depend on the material. We don't have many metals that we can use, a few coinage metals, and they can produce strong resonances. It means different colors when you look far away. And if you come very close to the particle, they're going to make very strong field enhancement that can be used for using molecule and things like that. There is also a side note on that, which is that if we want to now fabricate, if we want to not just use colloidal particle, but really fabricate nanostructure that will have plasmonic effects, we have some constraint. One of them is that the particle, the nanostructure, should be small, typically 100 nanometer or smaller. We need to control the dimension very well. We've seen that for the triangle, if we change a little bit the geometry, it's going to change the resonance. And of course, we have to develop technologies that will work for these materials. Have you got any question on that? Very general, brief introduction, something that's not clear. And if you feel like asking a question in French, don't hesitate either. I think you'll need to wait for the microphone or shout and I can repeat the question.
Hello, in the list of the elements we could use for plasmonic structures, you mentioned like the coinable stuff, but there's a big W. Where is it?
Tungsten.
Okay.
Tungsten, which we used to use in our old electrical bulbs, which is a metal as well, is also a plasmonic metal. It's a plasmonic metal in the infrared. And actually, it probably could find some interesting applications for light harvesting from solar energy.
Why don't we have a graph for tungsten? Is it too expensive?
Sorry?
Why do we not see a graph for tungsten? Is it too expensive to make experiments with?
It's in the infrared. So we have it, but it's somewhere there or even further away. So it's really beyond, well, at least 1.5 micron that it has its resonance. So it's useful indeed. It's not very strong, but it's far off in the infrared. Yeah.
Okay. Do we know the condition of what makes a metal plasmonic?
So the condition is just to have enough electrons. So that's this condition. And of course, if you think about it, what we would like is to have an effect possibly in the visible. So you probably know that all metals have a negative permittivity. But if you go to very, very long wavelengths, metal become with a permittivity that is minus infinity. So we are way, way down here. And that's, of course, not very useful if you want to do something in the visible. So you need a negative permittivity, but you want it to be close to this value of -2 so that you can have this effect. So this really constrains, unfortunately, the choice and the range where you can have plasmon resonance. You cannot have plasmon resonance at microwave, for example.
Why not?
Because epsilon is minus infinity, which is not going to do much for that equation here, where you would like it to be -2.
Okay, thank you.
Okay.
There is another question.
Thank you. I have a question, but I'm afraid that is out of the subject. It's when you are spoken about the blue sky. So when the sunset is going on, the layer of air is increasing and it's become yellow and red. But why the sky is never green?
I have no idea why it's never green. It's, okay, it's blue and not violet because of the physiology. So ask Dr. Rizzi tomorrow. And it's orange because of the absorption. A simple way to look at it is to say all the blue is going to be scattered away. And then when you just look at the sunset, you're going to see everything but the blue. And the way our eye works, and this is related to the 3 types of receptors we have, makes it appear orange. So the tricky thing is you cannot just take the spectrum and then think as a physicist would be in terms of spectrum. You have to translate that into physiology. And that's where things can get a bit more complicated.
Yeah, but I know that the eye is really sensitive to green. So I don't know why.
But it's a combination. The eye is never sensitive to just one thing. You have these 3 receptors, especially one of them, which is annoying because it's both in the blue and in the red. So it scrambles things up. That's also the reason why the sky is not violet, which will be quite fascinating. But it's really because it's scrambled. And also because there is high absorption for these short wavelengths.
Okay.
But I'm sure you'll get more answers tomorrow.
Okay, thank you.
Hello, I have just one question on this slide actually. So the different colors you observe here is what is the observation angle? Are they the same? Because you said that it's because of the scattering, right? So it's the same observation angle?
It is a dark field image, and here basically this is a dipolar response. So it's going to be fairly independent on the viewing angle, yes. So it's really because we have different resonances in the term of different optical modes, different plasmonic mode that can be excited, and that's why you get different colors. But if you look at this same sample straight or at an angle, you will see exactly the same colors. Yeah. I'll say a few words about how to observe these nanostructures later and how to, well, dark field microscopy, which is really the key tool for these type of systems.
Thank you.
Okay, so we can buy colloidal solutions and use them as they are. They've been chemically synthesized, or we can try to fabricate nanostructures. And that's actually the main activity in my lab, which is to fabricate nanostructures made out of plasmonic metals. And I'd like to say a few words about that. There are actually two approaches, one which is very widespread, the first one, and one that is, I think, now emerging and has some interesting advantages. The very widespread approach is called lift-off, and it relies on a so-called positive photoresist. So you start with your substrate, then you put some photoresist. Here we will put 2 layers of photoresist. I use MMA and PMMA. I mean, it's not very important, but what's important to remember is that these photoresists are positive photoresist. It means that when the electron from the electron beam right on the structure, the photoresist just goes away. And this opens up here a cavity in which, when you evaporate metal, gold, for example, on top, you're going to have the metal go through the cavity and being deposited here on the substrate. So at the end of the process, we do what we call the lift-off, which is to put everything in acetone, and that's going to dissolve the remaining photoresist, and then you will be left with only here the nanostructures that you wanted to have. For that approach, based on the positive photoresist, we use these 2 layers because when we deposit the metal, we want actually to avoid having a continuous film here over the edge. And so there is an undercut such that the metal film is not continuous and it only here cuts inside the cavities in the photoresist. If you don't do that, then you will tear your metal apart. So when you do the lift-off, there will be continuous film here, and then it's just going to break somewhere, which is not really controlled. So that's why it's important to use always 2 photoresists if you do a lift-off approach. The other technique, which I think is emerging now, and I think to some extent is superior, maybe sometimes a bit more complicated, is based on using a negative resist. A typical negative resist for electron beam is called HSQ. The difference is that wherever you write with the positive resist, it will make a cavity. And here, wherever you write with a negative resist, it's going to define the structure. So you see we have basically the complementary between the two. So the HSQ, once it's being written, it will stay here and it will be a very hard material. It's a bit like a glass, it's very solid. And then what you do is you bombard your structure with ions, for example, chromium ion, and you're going to etch away under the shadow, if you want, of this photoresist, such that at the end you're left with here the nanostructures you wanted to have. So in that case, we first put the metal, gold in that case, then photoresist on top. Whereas in the previous process, we first put the photoresist and then the metal on top. Now, does it make a difference? Well, actually, yes, it does. And if you compare structures, you have here always 2 columns. The left one is done with etching, and the second one is done with lift-off. And you see that with etching, like here, we've done 2 gold nanostructures with a very tiny gap. We call that dipole antenna, an optical dipole antenna. You see you can make a gap which is probably 10 nanometer and very straight. You can do that with etching. It's very hard to do with lift-off. With etching, you can do structures like that, which is just a spiral. It's impossible to do that with lift-off because the metal is not going to go away when you do the lift-off. So I think etching is very, to a large extent, superior for making very, very small features, say down to about 10 nanometer. The way etching works, actually, again, etching is a huge family, and etching is very much used also in semiconductor industry, which relies very often to something which is called not just ion etching, but reactive ion etching, in which you have ions that come onto your surface, but that are also mixed with some reactant material that will make a chemical reaction and take things away. So if you have here some gas that you can use that will react with the material you want to etch, you will be able to remove that very, very efficiently. So that works well for glass, for silicon. That's why it's very much used in the semiconductor industry. It doesn't work very well for gold. We start to see some emergence for gold, but it's quite tricky. So for gold, we've been using just this technique where basically you just bombard. It's like a focused ion beam, if you've heard about focused ion beam, but instead of directing the ions, you just bombard everywhere, and the mask will protect wherever it should not be etched away. Of course, when you do this nanotechnology, there are a lot of steps. Whenever you work with electron beam lithography, you first have, I mean, it's a very tedious and painful process, to be honest. So you first have to calibrate your system. You have to check that the dose you're using, the power, if you want, of your electron beam is sufficient to develop your structure, but not too much to make them too big or even gigantic. So there are a lot of steps that are required before you can really produce something pretty that you would be able to measure. So that's, at this stage, the summary. These two processes, lift-off, which is very widespread, used a lot, but I think produces less accurate structures, and etching, which is, I think, emerging now more and more, and allows you to control extremely precisely the features that you have in your system. And for both approaches, you still have some very tricky issues that you have to master before you can produce something you can really use. So that's so far for first introduction on technology. I don't know if you have some specific questions on that. It was all, yes.
Thank you. What happens if your nanostructure doesn't have a homogeneous material inside? So you have a varying material. What happens with the?
So in a few minutes, I will show you how you can make alloys. So alloys will be different materials. If you have a diversity of material, usually it will work with lift-off, because it doesn't really matter. With etching, and I think it will work also with etching, because with etching, you're going to protect the structure, and then it's going to work like an umbrella. And then irrespective of what there is beneath, it should be etched pretty much at the same rate. But it could be, and that could actually be a very useful thing, that part of the structure would be etched faster. And then you can make something which is also one of the holy grail of nanotechnology, which are tilted structures in 3D. So this is a possibility, yeah.
Another quick question. What about the implantation itself? So you're protecting your deposition with a mask, but at the edges, how much implantation can occur?
So it's interesting because when you do focused ion beam with gallium ions, people tell you always, well, and what about the implantation? We've actually never seen any damage related to the implantation. Bert Hecht in Duisburg University, he uses single crystal gold flakes, and then he processes the nanostructure using focused ion beam, and also there he doesn't see any damage. So I don't know, maybe these ions, they have so much energy that they go through, that's a possibility, and then they don't really damage your structure, or maybe something else magic happened, I have no idea, but we've not really seen any problem with that, yeah.
Okay, thank you.
Okay, so I'll go back to another facet, which is also important. As mentioned by Natalie, we do a relatively comprehensive approach to plasmonics. So not only do we do fabrication and optical characterization, we also do a lot of modeling. And modeling is also, I think, very important. And my feeling is that sometimes modeling is just limited to using COMSOL or whatever to make a pretty picture with nice colors and then sticking that into your paper. But I think, which is already nice and pleasant to view, but actually with modeling you can do much more if you try to go closer to your experiment. So I'd like to give you just a very brief hint about what we are doing. We've been developing numerical techniques for many years. The latest we have developed is called the surface integral equation, which is basically solving Maxwell's equation not in the derivative form that we maybe all know, but in the integral form. It's not very important anyway, the detail. The interesting issue here is that with that approach, you only need to discretize the surface of your object. So you just discretize, for example, here again, this would be optical antenna, 2 gold nanorods with a small gap in between. If you want to get the response of that system, then you just need to discretize the surface of the object. There is quite a bit of math inside, but once you've done the math, then you can have something that's fairly robust. The first thing one should always do if one works with numerical technique is to just try to check whether this is accurate or not. And this is a very tedious task, because we have very limited reference cases that we can use to check if the data is accurate. Actually, the sole reference we have pretty much is the light scattered by a sphere. For the light scattered by a sphere, we have the Mie solution, which you can calculate as accurately as you would like. And then you could compare your solution, here the dashed line, with the Mie solution, the gray line, and see as a function of the scattering angle, you have exactly the same results or a very minor error. And what's more important is that if you increase the discretization, so if you take smaller meshes, will your error decrease as well? Which is not always the case. You see here for another technique, sometimes you make a better mesh and you have worse result. Who is using COMSOL here, for example, or doing some calculations? Very good. Well, at least we'll have one challenge. If you try to do that with COMSOL, I think it's just a nightmare, but you can try, to try to look at the convergence of the solution for a simple sphere. So this is something that should be very important to do whenever you start doing some numerical calculation. And then, of course, you try to use your numerical simulation for your experiments. So here, this is again one of these small optical antenna with 2 gold nanostructures, a small gap in between. That's what we develop when we do simulations. And then we try to make very nice fabrication, and I've tried to convince you that we do, but sometimes it's not that fantastic. And this looks like more a pair of potatoes rather than this perfect structure. So, of course, the question is that totally useless? Should we just go back to the clean room and spend another 6 months trying to make something that really resembles that? Or should we try to use now numerical calculation to work out whether actually this would be a useful structure? And if you use a triangular mesh to discretize your system, you can do that. You can discretize it, and then you can compute the field, and you realize that actually this structure is fantastic because it has a very strong field confinement here between the 2 arms of the antenna, and that will work very well. So this is what I mean by going beyond using numerical simulation, not just doing the perfect calculation for the perfect structure, but taking your experiment, looking at your experiment, and then try to understand what you've really done into your experiment. And I think this is then very insightful. If you look at this structure, we can also now compare the perfect structure on the left column and the real structure on the right column. What we've done here is looked at the field intensity distribution around the particle. So it's like in a geography map, you unfold the surface of the Earth and you make something flat. So if you do that for this arm here and you unfold the field intensity, you end up with this type of field distribution. Here, these 4 corners, you see them here, very prominent, and these points here, they correspond to the further away. This is for the perfect structure, and this is for the realistic structure. You see the realistic structure is very different. Now, this was very close to the surface of the metal. I'm not going to go into the detail whether one should go so close to make field calculation, but I think a few nanometers is probably still okay. So we see that 1 nanometer this looks very different between the perfect structure and the real one. 2 nanometer, you still have some strange features specific from the perfect structure. And then it's only when you go quite far away, 10 nanometer, that the two look the same. So if you're having an experiment in which you've made a plasmonic nanostructures and you put molecule on it to look at Raman or fluorescence or whatever, and then you try to do calculations based on a perfect model like this one, and you think your molecules are maybe 2 nanometers from the surface, you see you build up a completely different understanding of the physics that's going on if you use this perfect model as opposed to a real structure. So again, going into the real structure, trying to use the numerical tool to mimic your experiment, I think provides a lot of benefit. There is also briefly a way to use this type of calculation to check the accuracy of your results. As mentioned, the only reference solution we have is just a sphere. If you want to check whether your solution is accurate for this type of structure, which could be here a real plasmonic antenna, you can use something which is called reciprocity, which you see quite a few papers about reciprocity around, and very often it's very misused. So if you're interested or if it's relevant for your field of research, I'd like to point out this very good paper from Christophe Callot from Leiden University, where he really discusses what reciprocity is. And then if I make a very crude shortcut, reciprocity means that if you have a system, you can, and you illuminate this system, you can exchange the illumination and the observation. It means that if you have a system and you put, say, a dipole close to this antenna and you look at the far field, you should be able to do exactly the same by taking the dipole in the far field and calculating the field close to the structure. It's a tricky thing because it is something which is vectorial, like most electromagnetic phenomena. So you have to choose the orientation of your dipole. You have to choose the same for the polarization when you compute from the far field. But if you do that, you should be able to obtain exactly the same results. And we've done that for the two structures, the perfect structure, perfect antenna, and the realistic antenna, by putting dipoles at different locations. For example, at the center of the antenna here, we put a dipole. We look at two orientations when the dipole is along the axis of the structure. This is what we call the X polarization. And you see there is a very strong field enhancement. If we look at the dipole that's vertical, so in Z direction, that's the green curve, there is no field enhancement. And the same is true actually for the realistic structure. And if you move your dipole around, then we see still some enhancement. It becomes more complicated because if you break the symmetry of the system, you have more modes that you can excite. But basically what you observe is that the overall enhancement, which is basically the scale we have on the left, is much, much smaller than what we have when we have put the dipole exactly in the middle. So if you are into taking a plasmonic antenna, putting a molecule on this plasmonic antenna and try to enhance some optical phenomena from your molecule, you better be sure that you put your molecule right in the middle of the structure. Otherwise, the enhancement is going to be very, very modest. Now, back to reciprocity. In all these graphs, you have color lines and you have black dashed line. The color lines, they have been computed by putting the source on the antenna and looking at the far field. And the dashed line have been the opposite. So we put the source in the far field, and then we look at the field in the gap of the antenna. And you see that they coincide perfectly. So that's another way of checking that your calculation is correct, because it fulfills something very fundamental, which is called reciprocity. You can still look at them like normal electrical engineers. So look at the field lines, although this is just a few 100 nanometer long. So if you go and do the experiments, the technique we resort a lot to is called dark field microscopy. It seems a bit of a contradiction in term because microscopy is all about light, so why dark? Well, the thing is, we have very tiny structures which normally would be barely visible. So dark field microscopy means that in the microscope, you take an objective with a high numerical aperture. So basically the light comes with many or goes with many different large angles. And we only illuminate at the center of the objective. So we only illuminate the sample here. And we don't look just at the reflected light because we would not be able to see our sample, but we look at the light that is scattered far away at very large angles. And this is why it's called a dark field microscope, because the incident light is blocked and you don't have any light directly reflected from the incident light. And with that, you can measure very small structures like a single nanostructure. You see here, these are structures that have an interesting response. We call that a Fano line shape. It looks like two peaks that appear. The structures are very small, typically 200 nanometer, but still you can very well observe them and collect their spectrum. So this is no problem at all. I think there is also maybe some misconception about the fact that normally in any optical system, there is a resolution limit, which is about the wavelength, so half the wavelength. And that is, of course, true. But it means that you cannot distinguish two objects when they are very close to each other. But if you only look at one object, like one single nanostructure, then you can perfectly well resolve it. And this is what we see here for these different nanostructures. Working with high numerical aperture objective has a price, however. These objectives, they are fabricated or designed such that they work only on very thin glass substrate, typically 150 micron. So it means that all the nanotechnology you do, you have to do on very, very thin substrate. And furthermore, you have to do it with glass, because you want to have something transparent. And this is very painful. This is very painful because most of these plasmonic metals, they don't adhere well on glass. So you make a structure. I'll show you an example in a minute. Well, I will show it immediately, actually. This is an example. We were trying to make electrodes that would work both for current and light. So we had here two small nanostructures that will look like a small plasmonic antenna. And then we want to connect them over very long distances. This is 140 nanometer. The gap is probably 30 nanometer. So it's very small. But then it's connected over 50 micron so that we can here plug in some electrodes and have some current go through the system. So the student, I think, worked 1 year trying to fabricate these electrodes. And he did. And in the end, he was quite pleased as he took them out of the clean room, although they are relatively rough. This is made out of gold. He just had time to take this same image, and then an hour later, the structure had disappeared. So that was extraordinarily frustrating. And he's been trying for 1 year. So he would fabricate that, rush out of the clean room and try to measure them, but within hours, the structure would just disappear, just vanish. We were trying to stabilize the gold onto the glass by using chromium as an adhesion layer. So a few nanometers of chromium, they will normally attach. That's the belief. They will improve the adhesion onto the substrate. But obviously, this was not working at all here. What's happening? I mean, it really looks like it's been just exploding. So that's very, very bizarre. We actually went back to the very old literature, not so old actually, but from the 70s, where there had been some measurement on some gold nanoparticles. And we all know that gold is a metal, so gold is solid, so it should remain solid. But actually, when you look at this ancient literature, you discover that when you go to very small dimensions, the melting point goes to almost room temperature. So something we think is just gold, is solid, is a metal. Actually, when you make a metal nanostructure, it can well be that if it's very small, it becomes liquid at room temperature. That's very mind-boggling, but it's true. It's true. Very strange. So Marco had a great idea of trying to look sideways and look actually at chemistry to help with his problem. And instead of doing like we all normally do, so put a small adhesion layer of chromium here, he decided to put a monolayer of chemical molecules, molecules that will have one hand that would attach to the gold. And this is done here with this thiol atom, so a sulfur ion here that will attach very well to gold. And the other hand that will attach very well to the glass substrate. And this is done here with the, oh dear, this silicon atom here, which have silane, that's the word, sorry, silane groups here with the silicon atom. So once you put this molecule on contact with the surface, the glass surface, this silicon atom or silane group is going to attach to the atoms of silicon that you have in the glass. It makes these so-called silane bridges between the two. And this is very, very solid. It will not detach from the glass. And this here with the thiol, with the sulfur atom, is going to attach very well to the gold. So normally we think, okay, nanotechnology, it means we work with metals, so we're going to have to use metals or at least inert materials to work for our entire process, but it turns out it's not necessarily true. You could very well combine this with some chemistry and do here this little monolayer, and the monolayer turns out to stabilize the structure very well. And then even after several weeks, you see the structure works well. We were able to measure them. We were able to look at the current that goes through this little gap. We were able to look at the optical response. So looking from another field of research, I think can be very useful, even when you do something very specialized, very narrow, and maybe you don't have this type of chemicals in the clean room, but go and talk with chemists and maybe they will help you with that. So that's, I think, the takeout message. Look sideways. I think that's really very important. And also at the nanoscale, materials can behave very differently. Gold becomes liquid at the nanoscale if it's a nanostructure. And this you find in the old papers. Now, I'd like also to say something because I dare to say it since I've lost all my hair. But every week we have a journal club in my lab. And every week there is a student that says, I've got this very old paper from 2015. So there is a huge value in the ancient literature. And I think 2015 is not such an old paper. We saw this paper about gold becoming liquid at the nanoscale was from 1975. So going and looking in this old literature, in papers that are actually not anymore reference, because when you reference article, when you write a paper, you just want to reference the possible referees, so you don't care about those that have passed away. So keep looking at publications that are 20, 30 years old. We can find them very easily nowadays with the Web of Science or Google Scholar. And I think this is very important. There is a lot of useful properties in sciences that have been forgotten. And we could make us progress faster if we would keep that in mind. That was my preach. I don't know if you have any question on this part of the technology.
Hi again. I had questions on the slide with the chemical structures. Yeah, this one. Could you explain the structures? What is a HS?
So it's a thiol group, so it's a sulfur and a hydrogen, and that's something that reacts extremely well with gold. So it's going to attach gold. Most of the chemistry, like when you do biosensing, with gold nanostructure, you use thiol, so this HS group, and on which you attach other things.
How do you call it? Thions?
Thiol, Thiol, yes. You can buy that by Sigma Aldrich, any chemical company. So basically there are two families, the thiol, they will attach to the gold and also to some other metals. And the silane, that's the group here, with this group here, they will attach to the glass or to the silicon as well.
So it's like glue.
It's like a glue, exactly. One hand speaks to the glass, the other one to the gold, and that works very well, and it's very robust. So the way you have to do it, you have all the details. We try to really publish everything in detail, so it's very well explained here, I hope at least. Otherwise, send me an email. You just incubate it overnight in a little container with this mixture, and it makes a self-assembled monolayer. So it's very simple technology as well.
I had another engineering question. If the ladder breaks, why do you not make just bigger?
Why do we have the breaks?
Like before it broke, on the before slides. Yeah, here. Why do you take such tiny branches size?
Okay, we want to have good optical response, so that's why we need to have a very small structure here. This is very small, and because it needs to have a well-defined optical response. And this is very long because we want to connect to a current source. And in the meantime, but this is still a bit preliminary, we've used that for doing trapping. So we've used dielectrophoresis, which is a system where you use AC voltage to trap object and then light to measure this object. And with that, we've been able to trap very, very small molecules. So we need the two, unfortunately. And indeed, this is challenging because something very high aspect ratio will be unstable. Yeah.
Yeah, I have a question on the slide you mentioned that when the gold particle really small, it can melt at the room temperature. Is that property applied for other metal material? And do you know why it does?
I don't know. We were lucky to find this paper, which is specifically on gold. I have no idea. It's thermodynamics. It could well be. I mean, if you think about it, other metals have similar crystalline structures, so it's likely the same would happen for them. But this paper is really very specific on gold. Possibly also because it's easier to measure because you have the nice optical signature. I think there is one here.
Hello, I have a little question on your slides comparing volume integral to surface integral method. And on the convergence of the two methods, do you think that the pretty poor convergence of the volume integral equation is inherent to the method, or it's more coming from a conditioning problem and can be solved by other numerical resolution techniques for the matrix problem?
So I think any numerical technique is good and should be used for what it is good for. I would advise to first test it. So on this simple sphere case, and it could well be that some commercial technique like COMSOL, rather Numerical, might be very hard to just do this test. But I think any technique is good, and any technique can be very useful. Just one has to be careful of using it right and testing it beforehand. Yeah.
Thank you.
So we have a few plasmonic materials, but not a lot. And actually, if you look at the literature, most research groups, they will use silver and gold, and that's it. Which means a response in the blue and a response here in the red. So we thought, could we actually extend this range and do something which is very simple, which is just to do an alloy. So mix these different metals. If you take just pure silver, it's going to be in the blue, pure gold is going to be in the red, and in between, we should have any resonances as we choose. And it is actually true, and these are measurements on materials we have fabricated, that if you change the stoichiometry, so the proportion of gold and silver, you go from silver here, which has the resonance in the blue, so epsilon -2 is close to the blue, to gold, which is in the red, and in between you can go for all possible resonance wavelengths as you would choose. The imaginary part is a little bit more tricky, but still there is some kind of logic on the way it evolves as a function of the stoichiometry. The problem is that when you do alloy, normally you do that at a very high temperature. And this does not work very well if you want to do nanostructures. Because if you do nanostructures like these little bars made out of alloy and you heat at 800 degrees to make alloy, then you see the annealing is just going to make them round, because this is what minimizes the energy, the thermodynamics of the system. It's a little droplets. So you want to make nice, well-controlled nanostructures, but you end up having just blurbs like that. So that's a bit annoying. So we thought, could we actually develop a technique that can make an alloy, gold-silver alloy, that would not destroy the shape of our nanostructures? And it turns out that instead of heating at high temperature, what you need to do is be very patient. So the recipe we came up with is based on heating at only 300 Celsius, but for 8 hours, and then half an hour at the very end to just give a little boost on the nanostructure so that you really have a good alloying process. What's also interesting in that approach is that you can just determine the composition by determining the thickness of the material you put. You can put 80 nanometer of gold, 20 nanometer of silver, and then you have an alloy which is 80% gold, 20% silver. Or you can put 20% of gold, 80% of 80 nanometers, sorry, of silver, and then you have this type of alloy. Of course, you're going to tell me, yes, but I'm very rich, and in my clean room, I have targets for the evaporator, which are all possible alloy composition. And of course, this is possible. You can do that. But these targets are very expensive. They last for years. And that's really not very optimal in terms of costs. But that will be, of course, an alternative, is to directly evaporate the right stoichiometry. Here, we just evaporate multi-layer, and we heat, but not too much. And the good news is that if we try to make nanostructures, the nanostructures are perfectly preserved. You see, we can make a small triangle made out of its 20% gold, 80% silver, and it remains perfectly triangular. That was before the annealing. This is after the annealing. And it is well annealed. We can look at electron dispersive X-ray spectroscopy, sorry, X-ray photos electron spectroscopy, which is here. We go through the thickness, and we see that through the material we have, in that case, 20% gold, 80% silver, and that goes through the entire material. Initially, we had two separate layers. Here we have just one layer. Or you can look also at the top at energy dispersive X-ray, and here you see that the two materials, they are perfectly mixed throughout the entire specimen. So, of course, a question, and I realize I forgot my accessory because I'm going to do an experiment, so bear with me. And before I do the experiment, I need to ask you a delicate question. Have you ever broken lampposts? Have you ever broken lampposts? I think nowadays students are really very good anymore, very good. We were also good, but well, I'd like to make a small excursion about resonances. So how would you break a lamppost? Well, don't repeat anybody that I've told you, but if you want to break a lamppost, you're not going to shake it like crazy with a lot of strength. You're just going to go on the lamppost, very gently press on the lamppost, and try to find the resonance frequency of the lamppost. Are you recording that? Oh dear. So you need to find the right resonance frequency, and then very gently press on the lamppost. And then, if you're lucky, you will have that. I'm always being amazed by the way I found this image, seniors walking across America. I don't know if it's the seniors who have been breaking that, but anyway. So it's all about finding the resonance of the system. And all resonance systems work the same. We've seen resonance, a plasmonic resonance in a nanoparticle, but actually this system, which is a spring and a mass, works exactly the same as a nanoparticle. So if you look at this mass and spring, and I start by agitating at a very low frequency, we'll see that when my hand goes down, the mass goes down. And when my hand goes up, the mass goes up. And we can do that all afternoon, nothing very exciting. But now if I change the frequency, and if I go across the resonance frequency of the system, you don't see it very well because the spring is a bit stiff, but what happens is that beyond the resonance frequency of the system, my hand goes down and the mass goes up, and my hand goes up and the mass goes down. So what's happening is just this. If you are at low frequency, before the resonance frequency, we are all in phase. But if you go at high frequency, we are out of phase. When the hand goes down, the mass goes up. So it means there has been a phase difference as we go across the resonance. And this is true for any system. It's true for the spring, but it's also true for a plasmonic nanoparticle, which is quite fascinating because it means that if you choose a wavelength which is below the resonance frequency, the incident light and the scattered light are in phase. But if you choose another wavelength, say higher energy, blue, for example, then the incident light and the scattered light are out of phase. So you are able, with a small metallic nanoparticle, to manipulate the phase of the light. And depending the wavelengths that you choose, you will either have scattered light that is in phase or out of phase. Now, this is actually the principle of most so-called meta-surfaces, these systems that are used to manipulate light using nanostructures. If you look at a grating, we all know what a grating does. Well, maybe you know what a grating does. A grating, it takes incident light with the parallel phase front and it directs it in another direction. So we know that the difference of phase between two successive phase front is 2 pi. So it means that if we have light coming here, at this point, the light continues, so there is no phase difference. But here there is a little bit of phase difference. You see, it acquires, it's like if it would jump a little bit such that it goes on the side. And further along, it will jump more until you reach the next phase front, which is here. And then again, between this point and that point, you have a phase difference of 2 pi. This is why some of these metasurfaces are called phase gradient metasurfaces, because there is a gradient of the phase between that point and that point. This works for grating, this works for a lens. If you think about it, the focusing effect of a lens is because here you have a phase of pi, here a phase of minus pi. And of course, the most general case is just a hologram, where you can produce any type of field distribution by manipulating the phase on the surface. So our idea was, can we use these alloy nanostructures such that we can mimic what's done here with the grating by just putting different nanostructures with different stoichiometries such that they will produce a phase gradient on the surface. And if you go back to what I've shown at a few slides back, this was silver, this was gold. If we do different alloys with different stoichiometry, we have different resonances. That's true for the resonance maximum, but it's also true for the phase. So if we choose to work at a given wavelength, the silver will give us the maximal phase, the gold will give us no phase, and any other material, any other alloy will give us another phase in between. And we done that to produce different metasurfaces effects. So the idea, again, there is a bit of technology involved. You want on the same substrate to put different materials. So you start by putting, say, nanostructures which would be 20% gold, 80% silver. Then you remove your photoresist, you start all over again. And here comes the tricky bit because you need to align for the second E-beam So you have to take it all out of the E-beam, you have to bring it back and make sure that the second E-beam is going to be exactly in between these previous structures. You can make another evaporation, for example, 80% gold, 20% silver, and then you remove your resist, you do the low temperature annealing, and then you end up with your nanostructures with different stoichiometries, and they're going to produce different phases for your incident optical light. So that's what it looks like. You can do that on relatively large area. If you look closer, it looks relatively neat. Of course, you're going to tell me, yes, but look, these guys, they're not aligned with those one. It's true. There is probably 20 nanometer differences, but you must remember that there are different materials. Some are 80% gold, 20% silver, and others are the opposite, 20% gold, 80% silver. So they have been done in two successive E-beam steps, one after the other. And if you use them, you can make holograms. So this is observation of a hologram. You can make lens, Fresnel lenses, and they will focus extremely well light here. Also, they work in the blue, so they work really with short wavelengths. For the Fresnel lens, this is what you have to do. You have to put your structures in a circle such that you have the different materials that will produce the different phases. So that's so far what we've just seen. We are, of course, very tempted to work with what nature gives us, but sometimes it's good to try to question that and see maybe we can use other materials. In that case, we've been using alloys. It takes time. I think it has taken 2 years to really optimize this recipe for alloy. But once you have it, then it opens a completely new field that you can use. And very briefly, so that was a short introduction to metasurfaces. I think many of them, they work by manipulating the phase of the light, doing that often by having different geometries, but you can also, why not, use different materials. And of course, if you have time and patience, doing multiple E-beam lithography allows you to put different structures, different materials exactly one next to the other. I think it's possible to reach an accuracy of about 20 nanometer in the position, and that opens, of course, many, many interesting applications. Any questions on that?
Thank you for the presentation. I had a small question, like you mentioned about using two alloys, like silver and gold. Have you also tried thinking like more than two?
So we've tried with other metals. Silver and gold, they share so many properties in common that they are very easy to alloy. We've tried with tungsten and gold. It also worked. We've tried with copper and silver. It also worked, but less well. So gold and silver seem really to be the material of choice that will very easily alloy at low temperature. Yeah.
And what about like alloy of three metals, like gold, silver, copper?
Possibly, yes. I guess if it's, I mean, it's known at high temperature to alloy gold and silver. If it's another material that would alloy well at high temperature, it's likely it would do the same, because basically what we are doing is mainly a diffusion. We let one material diffuse into the other. So if they alloy well at not too high temperature, it's possible that they would also diffuse in low temperature. Yes, that's a possibility, but we've not tried that.
And one more question I had was like, you started with the problem of it was very hard to make alloys, and then you thought of the idea where you could put like a small nano layer.
Yes.
So this, apart from this idea, you also had other ideas, or was it the one solution you just found?
First of all, I must say it was an idea from a very good Indian PhD student. She's done, it was her idea, like most of the idea I'm showing around, it's their ideas. And based on this mixing of metals, no, I don't have any other idea, but let's see on the poster session, maybe we'll find some exciting ideas together. Okay,
I have a small
you have a question, please.
about the use, the application in holography. So you mentioned that sometimes you have some shift of the position.
Yes.
How does it affect? So what's the spatial resolution that you need in order to control properly the phase over the surface?
Well, this is very deceiving because the tolerance don't need to be very high. First of all, if you think about it, we have a very primitive process because the hologram is discretized with only 2 levels for the phase because we have 2 materials. And the fact that we have a relatively high density of the structures, it will allow us to have a large magnification. But beyond that, I mean, you have here the numbers. So the particles are about 60 nanometer. The pitch here is about 300. But I guess you could have something larger, yes. We just took kind of standard dimensions that we were using for other nanostructures, I must say. We didn't think a lot about that in greater detail. Yeah.
Thanks. But it's impressive, actually, to get such a result.
I think there is an... Yes. Yes. You're very right. I've always been very worried that the referee would ask that question. Luckily, they didn't, but you're right. Yes. Yes. Very good. So now let's take a break. And then we continue. It's okay. C'est vrai, des plans? On continue alors. Ouais. So I heard you might get a coffee break afterwards. So I've been talking a lot about plasmonics and plasmonics, metal, strong. No, you're not let out yet. You have to sit back. Sorry. So plasmonics, metal, if you go back to electrical engineering, there is a way to look at these electromagnetic interaction in terms of multipoles. Usually metal, they have electric resonances, but of course, beyond metals, there are dielectrics. And over the last probably decade, we have started to see a lot of nanophotonics that is based on dielectrics, especially silicon. It was always believed that silicon would absorb light too much and you could not do anything useful, but it turns out that if you do nanostructures, the absorption is quite limited and you can really do nice things. What's also interesting with dielectric in nanostructures like silicon is that then they will have so-called magnetic resonance, magnetic multipoles. If you're interested in these different families, I'll just advertise here a paper we just published on trying to explain the different families of multipoles because it's quite a complicated zoology and there are many different names that exist and sometimes confusing. So hopefully this paper clarifies that. But we thought, can we actually benefit from the electric response of the metal and the magnetic response of the dielectric? And to do that, we of course need nanostructures that would have both metal and dielectric. So we did that. We use nanostructures where we have aluminum as a plasmonic material. We have silicon as a cylinder. The structure have to be relatively large. You see 400 nanometers. So we go a bit away from the very tiny plasmonics. And because the different modes, the electric and magnetic modes are going to interfere through near-field coupling, we thought we put also a little spacer here in between. So we put a little spacer of glass like this, we can adjust the distance between the two. So we fabricated these structures. You see here different views of them. The process actually is again an interesting process because it combines lift-off and etching. In order to make very vertical structures, you need to resort to etching. So the structure they are etching, and in that case, it's reactive ion etching to etch the silicone and the glass. And the mask that we use is the aluminum cylinder. So the aluminum cylinder is both going to be the metallic nanostructure that we use in our structure and the mask that we will use during the process. And this aluminum cylinder is done on top using simply a lift-off process. So we write here in the photoresist, PMMA in that case, the aluminum cylinder, and then we etch that through using it as a mask, hard mask for the structure. When we look at the optical response of the two parts, if you look at the optical response for the aluminum, you have mainly one dipole resonance, a very large peak, not very interesting. If you look at the silicone, you have many more modes that can occur. There are dipole, electric, magnetic dipole, but also electric quadrupole, magnetic quadrupole. So it's quite a complicated optical response. And then if you put the two together, it's what you have here, we have many, many more different peaks that appear. So as compared to the simple plasmonic nanostructure we had at the beginning with just one mode, one given color, now we have something that's much more complex in terms of optical response. So we thought maybe we can use that for biosensing. We did bulk refractive index sensing. The idea of bulk refractive index sensing is to immerse your structure into a liquid, and then if something happens in this liquid, the refractive index of the liquid will change, typically if there are molecules present in this liquid, for example. So that will influence the different spectral feature that you have. So you see here, these are measurements, different feature, like for example here, this black dot, when we go from having the structure in air, that's the red curve, or in water with an index of 133, or we add a little bit of glucose, a little bit of sugar in the water, that shifts the resonance. And the sensitivity of this measurement system would be determined by how much does it shift, how much does the wavelength changes when we change the background medium. So different features, different sensitivities. The best sensitivity we had was 208, and this is measured in nanometers, so it's the shift of the wavelengths when we change the background material refractive index by a unit of 1. So this is this refractive index unit here. So 200, we thought, okay, that works. We have something that can be sold as a sensor. Unfortunately, when we looked in the literature, we realized that it was not a very good sensor. Because if you just take a pure plasmonic nanostructure like gold, you can have a sensitivity which is about 3 times better. At 3 times the value, 600 nanometer, we only have 200 nanometers. So it's much more sensitive. The feature will shift much more than in the case of our complicated system. And for dielectric cavity, you can have something like 300. So that was disappointing. Nonetheless, we went back to our numerical simulation and we tried to understand why it was disappointing. And what we noticed is that this is the structure we're having. There is aluminum on top, there is glass, and here there is a silicone cylinder. And we see that the optical field is trapped inside the glass. And so these nanostructures, when they sense their environment, they do that through the near field. If the near field remains inside the structure, you cannot sense the environment. You need to make this near field go away, expel it from the structure. So we thought maybe we can do that by making this glass spacer a little bit narrow. And like this, at least in the calculation, we would have something where the field could go out and probe its environment. So we made the spacer a bit thinner. Experimentally, you can do that by having an additional etching step, wet etch, at the end of the process. And this is what you end up with. So it's not cupcakes, it's really the nanostructure. You have silicone here in blue. In green, you have the glass spacer, which is now a bit narrow. And on top, you have the aluminum. The aluminum is not very pretty, that's typical. Aluminum is very grainy when you evaporate it. It doesn't really matter in that case because the field is mainly horizontal, so it doesn't probe this graininess. but at least we could fabricate it and we could measure it, and it was a bit better. Not very good though, just an improvement of about 40 nanometer per refractive index unit. So a bit frustrating, but nonetheless, it was an interesting, again, an interesting experiment where we used the simulation to try to understand what's going on and to see if we could improve. And that's probably, again, the main message here. This loop between numerical simulation, fabrication, experiments, and again, maybe some additional numerical simulation that match better with what you have fabricated. And again, fabrication can be very, very stimulating. So I think these are the key points here. I don't know if you have any question on this type of hybrid structure. It's a field that's really emerging, and I think there is a lot of useful things to be done by combining metals and dielectrics. Any questions? That's the gym effect. You know, you're all exhausted. That's very good. Let's continue. Continue a bit towards chemistry, biology. I must say, as I mentioned at the beginning, I'm really impressed by this program you're a part of and the breadth of the program. We also try to do a little bit of biology, but this is really very much preliminary work. But nonetheless, I think I'd like to mention it here because maybe it can be of interest. So far, we have really looked at what we do in the clean room, so what we can call also top-down nanofabrication techniques. But actually, originally, plasmonics really came about as a field where people were doing chemical synthesis, so fabricating nanoparticles, gold nanoparticles, using chemical synthesis. There are quite a few reviews. I like this one because it's very illustrative. You can make all sorts of strange shapes just by chemical synthesis. By controlling the speed at which different facets grow, you can make tetrahedra, you can make all sorts of structures. The principle of chemical synthesis is always the same. You have, if we want, let's say, make gold, you have a salt, so a gold salt, and this gold cation, you're going to reduce them into a metallic version of gold. So you have some chemical, you have this salt dissolved in the liquid, and then you reduce them with a reducing agent. And then this transforms your ions into small, very tiny, solid, metallic nanoparticles. So you have all these little metallic nanoparticles. They're feeling a bit lonely, so what they will try to do is aggregate. So they will come and meet other gold nanostructures, and they will aggregate together. And they will grow and grow and grow and grow. And if you do this experiment very simply by just mixing these two components, you end up in your test tube with a black blurb at the bottom because you have something very large that will just absorb light. So it's not going at all to make nanostructures. Because of course, a gold atom prefers to be inside the material rather than on the surface because this minimizes its energy. So it will grow more and more and more. So if you want, so this phenomenon is called ripening. So to fabricate nanostructures, you need to stop this aggregation. And you do that by adding something which is called a capping agent. So it caps, it comes on top of the gold nanostructures in a way such that the additional gold atoms cannot reach anymore and it cannot grow further. So by balancing the capping agent and the salt, the reducing agent, sorry, you can basically decide the size of your particle. Capping agent, again, we will use these thiol-based capping agents. So it's got this sulfur group here. And by balancing these two elements, you can decide if you want small particle or large particle. And once you've made them, they are extraordinarily stable. If you go to Cambridge and visit the local science museum, you will still find this bottle from the time of Faraday. It's what he called his gold fluid. These are just gold colloids that Faraday made centuries ago, and that's still perfectly stable. So we were for some obscure reason, interested in seeing whether cells would be able to do that. So basically what we did was to take some gold salt and incubate the gold salt with some cells, different type of cells, the typical cells you can get, you know, cancer cells, circulating cell, different type of cells. And depending on the concentration of gold salt we would put, we would see nanoparticles appear. So for gold, they are reddish color. Nanoparticles appear in the solution afterwards. It's still very much work in progress, and there are a lot of complicated questions to answer, but maybe this could lead to something useful. So of course, what is going to be the reducing agent? Because we just put living cells. What is going to be the capping agent? Where are the particles produced? And actually these particles, once you have made them, are they going to be useful, and can you use them for something else? So I'm not going to spend too much time, but just give you a few hints where we stand right now trying to understand this. So as mentioned, we incubate our cells and we add the gold salt. And then after 20 minutes, we have some gold nanostructures that have been produced. Very surprising thing is that if we put a high concentration of the gold salt, we will have very tiny particles. We would have expected just the opposite. We would have thought, okay, if we put a lot of gold salt, we would have very large particles because there is a lot of material to be reduced, but it's just the opposite. So that was also a first surprise. But nonetheless, these cells, they are produced in these particles, sorry, they are produced inside the cell, and we can check that by using a microscopy technique which is called two-photon microscopy. Basically, we look at the fluorescence of this gold nanoparticle, and you see that when we have incubated the cells with the gold salt, they are full of nanoparticles. We can actually look further by using electron microscopy, and in that case, we see that these gold nanoparticles, they're little tiny black dots that you may see here. We've put green arrows to indicate them. They seem to be everywhere within the cell. So they go in the mitochondria, they go in the nucleus, they go in the membrane, they go everywhere. And this is quite surprising because, of course, interaction of nanoparticles like gold nanoparticles with living cells is something that has been studied quite a lot. But what normally happens is that if a cell is put in contact with something that annoys it, like a gold nanoparticle, it's going to make a little vesicle to protect itself from this invadant, if you want to put it like that. And these vesicles, you will mainly find them afterwards in the cytoplasm. So in very specific places. Here we're not putting nanoparticle in contact with the cell, we're just putting gold salt. And it's the particle itself, the cell itself, sorry, that produces the particle. And as mentioned, in the case of biosynthesis, if you call it like that, the particles are produced pretty much everywhere, whereas if it's just endocytosis, so the cell absorbing gold nanoparticle, they make this little vesicle and then maybe they aggregate together, and they are mainly in the cytoplasm. So it's still full of puzzlement. We are probably coming to some kind of a model of what's going on. What we notice is that the particles that we have produced like that, produced by the cell, they are not just naked gold particle, but they are covered with proteins. So they have proteins all around them. And if you analyze these proteins, you realize that they bear the signature of many different organs. So it means that the proteins we find are typical from the mitochondria, but also from the endoplasmic reticulum, from the plasma membrane, Golgi apparatus. So basically, it seems that these gold nanoparticles have been produced in many different places within the cell itself. So quite surprising. So as we stand right now, we believe that it's the fact that we put a gold salt is going to stress the cell. And as reaction, they're going to produce reactive oxygen species. So like when you go outside and smoke your cigarette, cadmium is going to produce in your body all these nasty poisons, like very reactive species like H2O2, hydrogen peroxide, which is relatively long life. And hydrogen peroxide can reduce the gold salt. So probably this could be the reducing agent. And then we have very nice particles that have a relatively homogeneous size distribution. So there must be some capping agent. And as capping agent, a good candidate seems to be a small peptide, which is called glutathione, which also has this thiol, so this sulfur atom here, which can attach to the gold nanoparticle and then protect it from growing further, such that the particles have all the same size. So that's where we stand. It's very much work in progress. I think it's quite fascinating to see that a simple cell can produce nanoparticles, gold nanoparticles. And our hope is that having produced them with a cell, they will be better incorporated by other cells because they have this protein corona on their surface. And these are some tests where we have produced gold nanostructure with a given cell, and then we look at the uptake by other cells. And contrary to what happens with normally synthesized gold nanoparticles, these ones seem to really go everywhere within the cell. So maybe they could be useful. There is some, now it's even more than research. There are some products around that use plasmonic nanoparticle for doing some chemotherapy based on the fact that the particles are going to absorb light and produce heat that could destroy a tumor. So we hope that maybe this type of particles could be useful for this type of applications. So that's again my short summary. Amazing to see that just a cell works as a chemical reactor. And of course, altogether, these chemical synthesis approaches are very useful, and you can do a lot of things. As you've seen in the very brief review article I sent, you can make all sorts of shapes, and you can produce kilograms of the structure, which is impossible to do with clean room technology. So that, don't know if you have any question on this brief excursion into biology. That's not the case. So I come to my final topic. We hear a lot about quantum science, quantum optics, which to me sound always very complicated. But anyway, I think light by itself is very fascinating. And probably the fact that light, the photon, has absolutely no mass, but has momentum and can produce force. I think it's already a very amazing quantum idea. And you can read more about that in this review, where basically a focused beam of light is used to trap a particle. And now this has really become routine technology in biology. For example, for moving cells around, we speak of optical tweezer. Like this, you can trap the particle just with light without touching it, without disturbing it, and then you can move it around and do whatever you like. So we've been also exploring that using plasmonics, and what we have done recently was to fabricate a small motor, a nanomotor. So how does this work? This is the way it rotates. So we have here in the liquid, sorry, need to find the mouse. In the liquid, we have one of these little motors, and when we shine light on it, you see it starts rotating. It's quite small. It's 1 micron in size. So here, this is an array of small little motors. And what makes it rotate, actually, this is kind of a small block of glass, which is a micron large. But what makes the motor rotate is that inside it has a little rotor, which is made out of plasmonics. So this is made out of gold. And when you shine light on the structure, it will start rotating. And it's very tiny because overall the rotor is only 200 nanometer. Now, in order to develop that, we have used machine learning. And I must say, when my student came and said, hey, we have to do machine learning, deep learning, everybody does that, I was a bit skeptical, probably too proud as a human, thinking that, come on, you cannot be more creative than our good old brain. And actually, the student proved me wrong, because indeed, using machine learning, he managed to develop nanostructures that are amazing and that work better than the one we had invented originally. As far as I understand, and I understand very little in this field, machine learning is very good at image recognition. So you can show images, and then it will tell you whether it's a celebrity or not, if it's written a book on the royal family or not, or it can even come up with new celebrity faces. So we've actually based our approach on that. We wanted to fabricate this little plasmonic rotor, which has a given shape. And for that, we basically used images of just one blade. You see, it's made out of 6 blades. We used just one blade and made images of these blades. And the idea was, can the deep learning propose shapes that would have a very high torque? So the torque is what puts something in rotation. You shine light, and then if the torque is important, it starts to rotate. Of course, we're working at the nanoscale, so the torque is very tiny. The torque normally it's a force time a displacement. So the units we have here is a force, but it's piconewton, and the displacement is in nanometer. If you put a lot of light onto your nanorotor, obviously it's going to rotate very fast. So you have to normalize the torque by the illumination power. So this is why we show always our torque here as a divided, normalized by the illumination power, milliwatt per square micron. We choose to just do all the optimization on one single blade, but then we fabricate the motor with 6 blades. 6 blades is a good compromise. We see that when we go from 1 blade, 2 blade, 3, 4, 5, 6, we increase the torque, so it will rotate better. But also going beyond 6 becomes quite challenging in terms of technology, because in that case, it becomes all very tight, and that's difficult to really get fabricated. That was the main challenge. We didn't want to just do the machine learning, but come up with designs that we would be able to fabricate afterwards. So what we did, using again our surface integral equation technique, was to develop a training set with, well, we have used 3,000 for the training and then 800 for the validation. So basically an image of one blade, then we computed with our conventional solution of Maxwell's equation the torque, and then we were able to associate with each image a certain value of the torque. And then this part of the engine was able to just look at an image and not say this is a celebrity or not, but say, hey, this will have a torque of that match, and this one is going to have a torque of that match. So the agreement is decent, I would say, between the predicted torque, you give an image, it predicts the torque, and the real torque that you have here. So that was the first part of the machine learning. The second part was, of course, to come up with new geometries. And for that, we use this deep convolution generative adversarial network, which basically kind of takes, as far as I understand, some random noise, tries to make a new blade, and then try to convince the engine that actually this is better than what it had seen previously. And this is where I was really surprised, because it turns out that indeed it could find better geometries. So in black here we have the original geometries with the original torque that we had in our training set, which basically have an average torque of 1 piconewton nanometer. And this is after a certain number of generations what was produced by the deep learning network. And you see that we have an increase for the average value of about a factor of 100. So it is able to make nanostructures that have 100 stronger torque. And also, if you look at the extreme, it can make some geometries that have a very, very high torque, as is shown here in this case. And unfortunately, some of these geometries, they are impossible to fabricate. It seems that you see very high value of the torque, almost 3,000 piconewton nanometer, but there are very subtle features that appear here, and this is not possible to fabricate. So we resorted to 4 geometries, which I show here. The first 2 are here. This one, you see it has a nice torque, around 980. We use actually a commercial optical tweezer from Tor Labs. It's a kit you can put together as an optical tweezer, and it has a laser at 980. The torque is relatively important, you see, minus 1,000. It's also interesting to see the spectral response of this system. I mean, this looks quite complicated, and this looks actually chiral, and one could think there might be a lot of high order mode, but actually, if you look at it, it's just an electric dipole. Most of the scattering cross-section is just built from an electric dipole. And this is true for the other geometries. This is the second one, and these are the other 2 that we have developed and fabricated, also with torques here at 980 nanometer. And always just a simple dipolar response. So fabrication, the process is again based on etching. At the end, you want to have a small block of glass that you can detach from your substrate. So what you do at the very beginning is to put a sacrificial layer. In that case, we use silicone as a sacrificial layer. You have to find a material that's not going to be etching the other one. So in this case, it was a thin layer of silicone that is etched at the very end, and then it will free this little block of 1 micron, well, 2 micron by 2 micron. On top of that, we had to fabricate the gold rotor. So this is done by etching. So we have again our photoresist HSQ. We illuminate with the E-beam. We etch away the material. Here there is an additional step. Sometimes it's annoying that the mask that you've used to fabricate the structure remains on the top. This HSQ, this photoresist, is so solid that normally it will stay forever. So it's very hard to remove. So again, a very simple trick is to put another sacrificial layer, and in that case, this is chromium. So you put chromium between the gold and the photoresist, and once you have fabricated your structure, you put a chrome etch, which will not attack the gold or the other material, and then that will remove the photoresist that you had on top. And then you define your block and so on and so forth. So these are the structures that as such once they have been fabricated. So very tiny rotor, probably the world's smallest rotor, about 200 nanometer, with some well-distinct feature. What was also quite interesting is that the yield is very high. On a wafer, we use 4-inch wafer, you put 90,000 such matters, and they all look alike. So this is the glass block. And inside, in the middle, you have the little gold nanostructure. If you make a cut, this is what you see. If you make a cut, you see here the gold nanostructure just in the middle. And on top of that, there is glass. For the focus ion beam, we had to put some platinum on top. Then we measured them again in the dark field microscope, and the fabrication is very accurate. So you get the same resonance at 980 as you wanted. And then, of course, we tried to see whether they would rotate, and indeed they do rotate. They will rotate faster if you increase the power. So this is what you see in the movie. We increase progressively the power, and they go faster and faster. Of course, the rotation speed is not earth-shattering. It's a few hertz, but it's still a world record for this type of motor, which actually is quite peculiar because, and I've not mentioned it yet, we would think that if you want to make something rotate, you just send circular polarization. And that seems to be obvious because circular polarization has some momentum and it will make the motor rotate. But actually, it's not what we do here. What we do is send linear polarization. So we illuminate our small motor with linear polarized light. We see that here, this is the pointing vector with the little arrows, and you have also the intensity on the log scale. This is why you have some negative value here. What seems to appear is that the pointing vector is going to be in specific direction, and you could think that it's like Newton's third law, you know, action-reaction. It will expel photons in one direction, so it will scatter light in one direction, and as a consequence, it will move in the opposite direction. And this is actually exactly what's happening in that system. First thing to check is that if you change the orientation of the light or rotate the motor, the force, the torque remains exactly the same. This is the case. Here we have superposed curve for different orientation of this light. So it's as soon as it starts rotating, it will continue rotating because the position of the rotor doesn't matter with respect to the illumination. Then what surprised us a lot was we thought, okay, now it starts to rotate because the light it scatters is going to be circular polarized. That seems to make sense. If the scattered light becomes circular polarized, then by Newton's third law, the structure should rotate in the opposite direction. So we looked here at the Poincaré sphere. Circular polarization in the Poincaré sphere should be here and here. And we see that the scattered light, as a function of the wavelength that's color-coded, remains perfectly linear. So this scattered light is perfectly linear. So actually what's happening is a very peculiar way of transferring the momentum, and it's something that has come since it's probably 3-4 years, is the fact that in addition to the spin, light has also some orbital angular momentum. And what we observe here is the fact that the scattered light is going to acquire some orbital angular momentum, and it's this orbital angular momentum that is going to make the system rotate. So it's a very minute momentum, if you want, and that's the reason why it doesn't rotate at very high frequencies, but nonetheless, it does rotate at a quite decent pace. Okay, I'm almost there. Last question, what did our ancestors do? I show you that and then take questions, is that okay? So did they put gold nanoparticle in the stained glass windows? Maybe we should vote. Who thinks yes? Who thinks no? Who thinks maybe? Who doesn't really care? Well, I think you would both be right. But let me just give you a little bit of background for that. We have, not far from Lausanne, a center for stained glass windows, which is an amazing place full of boxes that come from all around the world, from stained glass windows from many, many different places and very, very ancient places as well. And we were able to put our hand on a little piece of glass that comes from Germany, from the Münster of Ulm, which is in the late Middle Age and late medieval period. And then we thought, okay, this is red, this must be like gold. They must have put some gold nanostructure in the glass. So we took the sample, we cut it. This was very hard because these people, they were of course very frightened we would destroy their sample. And we had to take a little tiny corner, but you know, very, very little. So in the end, they allowed us to do that. We stuck the sample on a substrate of glass. And here you see a cut through the glass where we have indeed nice kind of reddish color. But then to try to work out what it is, we used EDX, so dispersive X-ray spectroscopy, and we were thinking, okay, we're going to find some gold. So we look through, we look here basically through the thickness of this material, and this is the analysis of the different components. There is a lot of aluminum because it's lime scale, it's an old glass, that's normal, that's known. But what was very frustrating is that looking for silver, which is in green, or looking for gold, which is yellow here, we didn't find any at all. So no gold, no silver, but And that goes back to the very beginning. We found copper. So copper is a less used plasmonic material, but nonetheless a plasmonic material. And if you look at the density of copper through the depth of this sample, there is good correlation with the optical image. And if you use, then we did electron microscopy to measure the size of the particle. They are small, 60 nanometer. They are extremely diluted. The space between one particle and the next one is almost 4 microns. So this shows how strong these colors are. Very tiny 60 nanometer particle, very diluted, but nonetheless, it gives you this very nice color. We try to push it one step further and looked at the mis-scattering. So if you do mis-scattering for a 60 nanometer copper particle, you have actually a fair amount of absorption because it's small. And from this spectrum, you can obtain the color. And if you put the color in the CIE diagram, you have actually a fair agreement between what we have here from the calculation and what we have seen on the sample. So indeed, yes, they were putting some plasmonic nanostructures, but it was not gold. It was not as magnificent as gold, but it was copper. So that's the final summary for what we've seen on the machine learning. And I'm also happy to take questions on that if there are